Hello, we're Team 19, and our project is the breast cancer survival prediction.
My name is Mark Garbon.
My name is Maria Santiago.
And I'm Diego Zavala.
So for our project, we focus on the issues of breast cancer, which remains one of the leading causes of death among women worldwide. A key challenge that many cases are diagnosed at the late stage, which significantly reduce the chances of survival. Early detection can make a critical difference in treatment outcomes. However, many people are unaware that symptoms and lack of awareness contribute to delayed diagnosis and higher mortality rates. Our work aims to explore machine learning can support earlier identification through data. So for our objective was to develop and compare the performance of multiple classification models to predict a breast cancer patient survival outcomes. We wanted to assess which model was the most accurate and consistent when applied to both balanced and unbalanced data sets. This allow us to explore how imbalance affects model prediction and how balancing can improve outcomes.
Our original plan was to work individually throughout the entire process, which included data exploration, pre-processing, and feature engineering. The approach that we took instead was to explore the data set and see all the features in the data set and what type of variables were included in those columns. We also performed feature engineering and encoded categorical variables. The feature engineering allowed us to see which columns had more importance and would contribute more towards our models. We also decided to balance our data set to eliminate bias towards patients who are alive. And we used four different classification models, including Gaussian naive Bayes, random forest, k-nearest neighbor, and logistic regression.
So throughout our process with this project, we learned a lot of key insights on while performing our hands-on experience with various machine learning techniques. The first thing we did was performing initial exploratory data analysis, which helped us get a key understanding of the distribution and the structure of our data set. Next, we did feature engineering, which allowed us to identify the most relevant variables for our project and allowed us to move forward with how we wanted to model our classification models. Another thing we did was engineering a new variable from an existing variable, which was we created the survival years variable from the survival months variable by rounding up the months into years and then binning those into further different splits. We also managed to test models with different splits, which allowed for different results depending on which models we were using.
So for my individual contributions, I created visualizations for the exploratory data analysis, which gave us more visuals on which columns contributed more. And then I also performed feature engineering to see which columns were more important. I balanced the data set by having the same amount of alive and deceased patients. And I did this by copying the amount of deceased patients to equal the amount of alive patients, which the alive data set had about 3,400 patients. I used three different classification models to see which ones would achieve higher accuracy in both the unbalanced and balanced data set. And the models that I used was k-nearest neighbor, Gaussian naive Bayes, and random forest.
My main focus on the data was the data analysis and model testing side. I started by analyzing the data to understand which feature might be the most important for predicting patient survival. I also look into what each feature meant and how it could affect the model. And by balancing the data sets by unsampling the minority class, which helps improve the performance for predicting patients who didn't survive. This made a big difference, especially in the recall scores. By removing the status and survival months columns to test how well our models could perform without the direct information and still run the classification. So compare balanced and unbalanced data sets. We tested different models like the random forest, K-nearest neighbor, and logistic regression, and ran models with a different train split, like 50-50, 70-30, and 90-10 to see how the result can change.
For my individual contributions, I primarily worked on the exploratory data analysis throughout the beginning parts of the project, which included just summarizing how many, like the counts of the numerical data and the different unique values for like categorical data. I also encoded the categorical data to prepare it for classification models. For feature engineering and analysis, we did this to see which and features would be the most useful for our variables. I personally worked on the random forest classification only. I did this by experimenting with different survival years bins for 5 and 10 years, 3, 6, and 9 years, and then 2, 4, 6, 8, and 10 years, just to see which ones would have different effects depending on how the years would be split up. For deliverables, as we said, we worked with 4 different models being Gaussian naive Bayes, k-nearest neighbor, logistic regression, and random forest. We tested these models on both the balanced and the unbalanced data set to have no bias for the alive patients, which had a much higher rate. Here are results from the best models that we had. For random forest, the unbalanced we got 84% accuracy. For the balance was 94. For KNN, we got 86% unbalanced and 91 balanced. For the GMB, Gaussian Bayes, we got 85 unbalanced, and then it dropped for the balance, which was 64. And for logistic regression, we got 88 and 77 for unbalanced and balanced. Thank you to Professor Alireza Abdoli for being our mentor, and to Professor Butsu for giving us guidance throughout this whole project, and also to National AI Campus for allowing us to do this project and take it on.